All right, welcome everyone. Welcome to the Industrial Cybersecurity Zero Touch Provisioning virtual conference. I am Lucian Fogoros, and I'm actually the moderator for the session. And I'm supported by my team members, Carolina and Greg. And today we have an exciting panel from representing companies such as Intel, Mocana, and ARC Advisory. For those of you that may not be aware about IoT World, we are a digital publication that covers the economic and technological implications of the transformation taking place as industrial IoT proliferates throughout the enterprise. We combine journalistic coverage with data analysis and expose the stories, players, trends, and innovations that shape the industrial IoT. As mentioned to you, this webcast is designed to be a virtual 100-minute conference on a topic of secure provisioning for industrial devices. IoT Industrial Cloud systems are rapidly maturing as packed systems that can sense, collect, analyze, and action on edge devices. However, the software-based device security and manual proprietary provisioning methods delivered by platform providers are preventing deployments from scaling. In this webinar, our distinguished speakers decompose the industrial data pipeline and demonstrate where device management security services instrumented for hardware security can be applied to build a connected, secure security model that tests, provisions, updates, and manages devices. Automated secure device provisioning without human intervention is the key to scaling element to place more devices into service to accelerate the value from industrial cloud. We welcome questions from you leveraging the hashtag ICS_IIoT on Twitter or leveraging the chat box. And so we'll start the first session on industrial impact on industrial and OT cybersecurity. And this will be conducted by Sid Snitkin, the Vice President of Cybersecurity Services at ARC Advisory. He has been on board with ARC for over 20 years and comes with a wealth of experience over 30 years in industrial automation, information systems, and manufacturing, with particular focus on metals industry. He's got a Bachelor in Science and a Master's in Science from the Carnegie Mellon University, and MBA and PhD in Operations Research and Artificial Intelligence from the University of Pittsburgh. Sid's session will focus on global trends driving industrial IoT adoption, implementation goals, strategies, and cybersecurity concern, and what's needed to secure, enable industrial IoT. Welcome, Sid.
Thank you, Lucian. Good morning, everyone, or good morning, afternoon, or evening. I don't know where you may be. As Lucian just said, I want to talk to you today about IoT's impact on industrial OT cybersecurity, and I'm going to do it in a few steps. First, I want to talk about what we call digital transformation, and a lot of call industrial IoT, but it's all centered around IoT. So that's, you're going to use that term a lot, so I don't want to confuse you. And I just want to frame what's happening in that world. We see an awful lot. Then I want to talk about the impact that this is having on industrial systems, both IT and OT systems. Then I want to get to the point about the effect that has on cybersecurity and what's needed to address that, in particular around the IoT devices. Oops, there we go. So to begin with, you know, at ARC, we're seeing a real surge of interest in digital transformation initiatives. And to be frank, this is occurring across our broad base of industrial clients, as well as around the world. We have offices in several parts of the world, and we see it everywhere. And in our energy practice, for example, we're getting requests for support around digital transformation from large oil and gas operators, power companies, and even things like new entrants into the alternative energy market. The same is true in our manufacturing practices. And this includes process manufacturers and things like chemicals, metals, and pulp and paper, discrete manufacturers in automotive and aerospace, and hybrid manufacturers in everything from pharmaceuticals to food and beverage. Our practices in smart cities and logistics also are reporting similar levels of interest from city planners, owners of smart buildings, and transportation companies. Now, these digital transformation initiatives, and again, you may call it industrial IoT, there's lots of terms for it, but these efforts are all being driven by three major technology changes. First, of course, is IoT. And when I say IoT, I'm talking about all kinds of devices, everything from process sensors and video surveillance systems to smart assets all over the corporation. And then the second major trend is analytics. And I'm not personally, that's my background is in operations research and analytics and AI, so I really like to see that. But analytics is really getting a large interest in companies. And when I say that, we're talking about platforms, whether they're general platforms that might be based on something like AWS, or it could be more specific type of support packages, analytic packages from companies, you know, with products like Predix, MindSphere, or EcoStructure. And then the third part is the cloud apps. You know, everything's moving to the cloud these days, and that in that category, I'm talking about conventional applications that have been converted to the cloud, or a lot of new cloud apps just to do specific things, new business ideas and everything. Now, while many of these efforts are focused on smart operations and maintenance, one of the ones we see the most is predictive maintenance. But we see the same thing happening across all the activities of an industrial company, things like smart supply chains, smart services, smart design and build of new facilities, the construction of plants and things like that, as well as in the design of smart products. And the benefits that these companies are expecting, and some of them are already getting, are very diverse. You know, this includes things like reduced costs to design, build, and operate and maintain facilities, increased productivity, longer capital asset lifetimes, which is incredibly important in the industrial world, safer and cleaner operations and products, improved and enhanced service offerings that they can offer now, as well as it's enabling a whole new range of new business models and new business opportunities. Now, the first impact, the impact of all of this, these are the trends, but the impact they're having on my area, which is industrial control systems and things, or industrial, control in general terms, is on the architecture of these systems. It's the first place you see it. And on the left on this slide, what I'm showing you is a traditional kind of industrial architecture within an industrial company. You know, at the top, you have a corporate IT system, which is generally kind of in corporate data centers, and it's really designed to support a lot of activities within the company. And then at the bottom on the left, you're seeing all the plant OT systems. And as I assume many of you know, these are generally made up of very specialized proprietary devices, and they're isolated as much as possible from the external world, I mean, for cybersecurity reasons in particular. And at most, they might have limited connectivity with business systems for the exchange of production plans and historical data. Now, on the right is the architecture we're seeing emerging. And this is being driven very much by the desire to implement digital transformation programs. At the top of this new architecture is a cloud environment. And this includes cloud versions of traditional manufacturing applications like ERP and PLM and SCM and things like that, EAM. But it also includes a powerful analytics and support for internal and external users, so that now you can connect more with suppliers as well as customers. And many companies also have what we call an IoT platform. And this is to manage the connectivity between this cloud environment and all the company's resources, the many operating assets that you see at the bottom there. And it's going through complex networks with edge systems. There's all kinds of designs today, and then who knows what tomorrow will bring. And when I talk about, and one of the key points I want to make is that this architecture is really being built in anticipation that the assets that the companies use for whatever their operations may be are going to be smarter in the future, and they're going to provide an extensive amount of information about what their condition, their operation, their progress, and what their performance is, and things like that. And when I say that, there's a wide range, and this is going to impact a very wide range of assets, everything from like mobile mining trucks, for example, are now today very smart and already have their own control systems on the trucks. At the bottom there, you see that little thing that you probably can't read is really an industrial control system in the future. And notice it's quite different than the design you see on the left, even though you can't read it, I'm sure. It's impacting the machines and the equipment that industrial manufacturers use, like packaging systems and machining centers. It's going to impact the basic elements in a control system, like pumps are going to become smarter and things like that. And it's also going to include a lot of just general kinds of sensors, more sensors of all types to measure all types of environmental situations and to give more context to the data that they're collecting. Now, let me go a little deeper into this individual asset type of a thing, because I think the implications there are quite significant. And these are the things on the bottom on the right of the slide I just mentioned. And if you look on the left there at the top, this is that picture you couldn't read, which is an industrial control system. And that's the future kind of design. And this is being promoted by lots of organizations, open process automation type systems and things. And the key things to note about it, in the past, manufacturers or industrial companies have always expected their automation suppliers to provide safe and reliable control systems. And now today they're also saying secure. But they're also expecting a lot more in the future. They're expecting these systems to be designed for connectivity and intelligence, to be built upon advanced updatable IT technology. Updatable is very, very important in the industrial world because of the legacy system problems and the costs of replacing equipment, as well as built to enable seamless integration with cloud apps and data in the architecture I just showed you. On the right there, you'll see what I mean by a machine. There's lots of terms for that, but this might be provided by an OEM manufacturer, and it may be. I don't know exactly what that machine is for. It's a nice picture, but it could be something for packaging, it could be for etching, it could be doing lots of things. But in the past, these kinds of systems from OEMs would come, this is a big piece of equipment, would come with their own control system, and that control system would be built out of individual discrete components, maybe PLCs for control of the motion, and there may have separate motion control that actually does the positioning very accurately. Could be vision systems, HMIs, but they would always be individual discrete components. Today, what we see happening is all of that's now being put into a single box, with multiple processors and a virtual operating system. And that one box is now going to do all of the functionality of all those pieces above. And so we think that's a very positive development. One reason is because you can upgrade it, it's more advanced technology, it's going to be much more secure and things like that. And one point I want to note though, so in a way you're going to see these machines are going to go from many pieces to a single box. And you may think, oh, that's great because that's going to reduce the connectivity issues, which is one of my big concerns because of cybersecurity. But the reality is that now you're going to probably have bigger connectivity issues because within that single box are going to be lots of different applications. And these boxes are getting smarter, more things added to it, AI type systems and things like that, about functionality for security and functional safety and things like that. And these apps now are not only going to connect to a control system, which is what they used to do, would be a single connection or a few connections, to now they're going to be connected to lots of different systems, to the cloud, to vendors who are going to do maintenance and things like that. So actually, this is a very big issue to consider, is you have to provision and secure every one of those kinds of apps in that system. So that's kind of where we see the technology going for control systems, well, IT and OT systems in the industrial space. And now let me shift and talk about security specifically. Everybody understands the advantages, I think, of IoT today, these IoT developments or digital transformation. But many industrial companies are still worried about the potential security risks. And then when I say companies, I mean the boards of directors and things like this. Because it's adding to, and they see the security risks of IoT as something that's adding to an already high level of concern with cybersecurity, by board members and things like that. And these concerns are being driven by reports they read in the news. It's a daily thing. Many of my clients will tell me, oh, our CEO just read this and now he's concerned about something, and rightfully so, I think. But for example, there was a recent article in Forbes that discuss the impact of NotPetya on the logistics giant Maersk. And it showed the boards that the cost of a single incident can be just enormous. In the case of Maersk, it shut down their operations for days, and it cost them overall, they figure, around $200 million for a single incident, which was actually almost accidental. And then last year's attack on the Ukrainian power grid is fresh in the mind of every critical infrastructure operator I talk to. And this is causing many to question the ability of their defenses to stop a sophisticated attack by malicious state actors. They're worried about that. And then everybody's worried about ransomware. It's a major concern for every organization. Today it's a concern for us individually. In my own company, we were just talking yesterday about how we're going to protect ourselves if somebody loses a PC to ransomware. But in the industrial thing, the fact that these kind of attacks like WannaCry that happened a while ago, actually included industrial companies like Nissan and Renault, and this brought their operations to a halt. And so this kind of is telling boards of directors that no one is safe from cyber criminals. So I think these are justified concerns. But these justified concerns, when you add IoT cybersecurity to it, the issues there are really having an enormous impact on the digital transformation initiatives. And the fact is, this is hurting everyone. First of all, the companies, the individual industrial companies, are not getting the improvements that they need to stay competitive. IoT suppliers and distributors of these products that could help them get these benefits aren't able to sell their products, and that's really keeping them from investing in new products and better products. And then you have the OEMs that I was talking about before that make things like machining centers and things. And these companies are losing opportunities to distinguish the value of their product through more functionality and more visibility, as well as the money they're losing from their service business. And again, this is going to keep them from developing more reliable products. So concern about IoT cybersecurity is incredibly important. Now let me talk about the kinds of things that people are concerned about. What's driving this concern? And this is a chart that I took from a recent study by the SANS Institute this year. It was done earlier this year. It was published this year. And it was about industrial IoT security. And it was sent out to hundreds of different industrial companies participated. And this included both IT and OT people. If you're familiar with SANS, you'll know that they have a big practice and training in IT as well as in OT systems. I'm using this because I was honored to be able to, I was asked to write a prologue to this report. We happen to collaborate a lot with SANS on the industrial type of cybersecurity. And as you can see from this chart, companies are worried about all kinds of, the drivers for their concern are things like protecting the data, the confidentiality of their customer data, their own company data, the privacy issues and things like that, protection of equipment and systems, protection of the company itself against financial losses through damaged assets or disrupted operations, which could damage their brand. They're concerned about compliance with industry regulations. They're concerned about the impact it may have on reliability, availability, efficiency, and productivity of the operations. Safety is another major concern. And the thing I wanted to point out with this slide in particular is these are concerns that are shared by IT and OT people. Now, if you look on the right side, you'll see that the rankings are different, but that's kind of expected. You know, IT people are, their primary concern is protecting the data, where if you go down and look at like safety, for example, that's only number 6 on their scale, where it's number 2 on the OT team. The OT team is more concerned about keeping operations running. So these are the things they're concerned about. This is driving a lot of this concern with IIoT cybersecurity. Now, the thing that's justifying these concerns, I'll say, or adding to these concerns, is that people realize that IoT devices are at risk. And the kinds of things that they are worried about happening that place the devices at risk, on the left you'll see this was how many people were concerned about certain different issues. And the ones that were very high on the list, I don't want to say they were the top, I don't really recall. But again, this is more data from that same SANS report. But 48% of the respondents, again, this was hundreds of industrial companies, are concerned about the lack of security considerations in product and system installation, configuration, service, support, and maintenance, which is really a key issue in this webinar, by the way. Now, 39% are also concerned about what everybody tends to think, which is the security of the design and manufacturing of the IoT products. And there are many companies, and there's just about the same amount, are concerned with the pace and the lack of updates in maintaining the security of these devices. And so this is what's driving a lot of the concern with the security of IoT devices. And I think, you know, that shouldn't surprise any of us because these are common issues we all know about. You know, we see every day, we see insecure devices. We certainly hear a lot about devices that were never provisioned properly. One thing I do, I mean, this goes back a long time. One thing I've seen in industrial plants is that there'll be PCs with security capabilities that no one's ever enabled. Either because they don't know how to do it, they don't have time to do it. It's a very time, in particular, let me mention that, you know, provisioning of a device, whatever that means is going to vary by device, but it takes time. It can be very complex. And if you don't, and in things that are complex, I'm speaking from the industrial world now too, in particular, I guess, people don't do. If it takes too much time and it takes certain expertise, it won't get done, and no one will know it didn't get done. And so what you end up with is you have a lot of devices that could be secure, that are in operation, that are not. We all know about default passwords. I mean, a password, I think, is the most popular password. If it's not admin, maybe in industrial space, it's admin. They all come with default passwords and no one fixes them. And then we all know about delayed updates on vulnerabilities. There's a lot of vulnerable things. We all know they're vulnerable, but we don't have an update to fix them, or nobody is taking care of that. And, you know, the real world threats that we read about and hear about reflect all these issues. You know, there's things like the Mirai botnet, or there's Heartbleed today. And those are all reasons why people are concerned about the security of devices, which I would call IoT devices in today's world. And just a comment, if you look, and I make the point there is, you know, this thing of insecure, one thing is true in the industrial world is there's a history of dealing with insecure devices because much of the OT world in particular has a legacy, a lot of legacy products, and they just weren't designed with security in mind. So they're very concerned about the security. And again, I think rightfully so. They've dealt with this for years and they continue to deal with this problem. Now I just want to close with my comments about what's needed to secure these issues and to address these concerns. Now, I think everybody, hopefully, but from my discussion or from your own experiences, you agree with me that IIoT or IoT cybersecurity is a root problem that needs to be addressed. It all comes down to the devices. But I suspect that many people think that the solution is simply getting people to do secure devices. You know, I see a lot of work being done by organizations like the IIC. There's a secure framework that's been developed to help tell people how to design secure devices. There's companies that are getting into the certification kind of business to certify that devices meet those requirements. And that's all good. I think it's wonderful. But just saying I have a secure device doesn't mean that you have the security that end users need. You know, industrial concerns go beyond ensuring that the purchased IoT device is free of latent vulnerabilities. Industrial companies need to be sure that these devices are securely deployed and connected to their cloud systems, this cloud environment I just described. And they also want to be sure that the security of these devices is sustained, because that's a major, major issue. So to do that, you need to really address IoT security, you know, from the edge to the cloud, from the manufacturer to the end user, throughout the whole life cycle of the operation. Now, this slide right here, I think, captures all of those issues. This is a slide I borrowed from Intel, and they're going to be speaking later. And I think it does capture a nice way to frame the extent of security issues that need to be addressed. And the fact that these are not being addressed is a major problem today. and it's going to continue to be a major problem. And just solving the problem of the secure device is not the sole answer. It's important. It's necessary, but not sufficient. You have to make sure that's done, but you also have to make sure that these devices are deployed and provisioned properly and everything else. And as you're going to hear, there's a lot of issues in getting that done. It takes time. People don't have time. There's other logistics issues of when things are done and so on that impact doing this the right way. And I'm going to now pass the discussion over to Guy Lee from Intel, who's going to tell you about some of the things that Intel is doing and Mokana are doing to address these issues. So thank you.
Thank you, Sid. And if you're just joining in, this was Sid Snitkin at ARC Advisory Group on the IoT's impact on industrial and OT cybersecurity. In the next session, we have, stay tuned, we have a couple more speakers lined up. So Guy from Intel, as well as Dean Weber of Mokana, and then we have a panel discussion, so feel free to enter your questions in a chat area or on Twitter. So next session, it's on zero-touch provisioning and security to scale the industrial cloud. And this will be done by Guy Lee of Intel Corporation. Guy is a computer industry veteran with over 30 years of experience in computer architecture, hardware, software, energy, security, and IoT, and has a Master of Science in Computer Engineering. He's the product manager of IoT security at Intel Software and Services Group. Welcome, Guy.
Thank you very much, Lucian. Can you hear me okay?
Yes.
Yeah, I just want to thank Sid for taking us through the big picture here of what we're all worried about and how that really is the Internet of Things is really feeding this digital transformation. And one of the things that's critical in that is securing those systems that we're putting in place. So we've talked about the big picture. I'm going to zoom in on a very specific issue, which is what we're all here for today in terms of how to provision devices, get them onboarded in the system, up and productive for your industrial IoT, and really talk about the first minute of the life of that device. And then after I'm done, Dean from Mokana is going to go through and talk about how you manage the rest of the security life cycle on that device. But I just want to talk about the first minute and how critical that is, because I don't know if anyone saw it, but about a year ago there was a gentleman did an article in Atlantic Monthly. He stood up an Internet of Things device. He just rented an AWS machine and a Linux machine and put it up on the internet as an internet toaster, and just measured how long it took for people to notice it was there and actually start probing and attacking it. And he lasted about 43 minutes. And what we're seeing today is that it's taking it some folks longer than 43 minutes to get their devices installed, secure, and up and running on the Internet of Things. So it's really critical that we're able to address that, and especially in the first minute of life. And I mean, there's not a big secret to that. If nothing else you walk away from today, I want your new mantra to be the 3 things you have to do to harden your industrial Internet. And that starts with hardening the device, securing the communications, and then managing and monitoring everything. And the good news is we've got 30, 40 years of experience with the internet. We already know how to secure the comms. We know how to manage and monitor. What's really new in this is hardening the device and making sure that it's hardened and secure from the first boot. And then within hardening the device, it really comes down to having hardware-based security, a root of trust identity in that device. That's a very base principle. And then on top of that, you put a secure boot, some secure storage, a trusted execution environment, because even operating systems have flaws in them. So you need something underneath that's more secure. And then the last thing you can do on top of that is actually do application whitelisting. If you've got an Internet of Things device it really only has one purpose in life. Maybe it's got a couple of them, especially if you start looking at those machine centers where you're doing virtualization. But it's a finite number of things that have to run on it. And application whitelisting is just the converse of antivirus. You know, we'll blacklist something we know it's bad. Whitelisting is we allow the machine to run only the things we know are good. And if you're able to do that, then you can secure your Internet of Things. It all starts with that identity and that hardware security. So let's look at what's going on today. And one of the big trends you're seeing, and even has been identified on the Gartner hype curve, that it's to the point where it's ready to deploy now, is device security being done in hardware. You know, we're used to the PC server world where security is done in software. At the industrial level with the Internet of Things, you really need to be worried at the hardware level. Security is compute intensive if you want to do it right. If I want to do crypto, if I want to do protection, detection, it really works best with security. And you know, you think about an Internet of Things device that's running on battery, it's actually less battery for a device to wake up and do some crypto in hardware and then go back to sleep right away. The faster it can get back to sleep, the longer it can last on that battery. So here we're just showing the functions that are getting converged into intelligent devices on the top. And you know, these are things that are really there to address performance or requirements of the device. You know, things having to do with latency, with networks, and then you know, just the intelligence to do things smarter and more distributed control locally, so you don't have to move the you know, huge amounts of data. In fact, probably more data than you've got bandwidth to move up to a cloud back, and really take care of that and take advantage of some of the things that we've developed on PCs and servers, and actually move those down closer to the edge and in the industrial Internet of Things. And the things that you're seeing becoming available in the devices that are able to run at the edge really include the security functions. And so you're seeing things like encryption engines and non-volatile storage and communications, all of those things being integrated into the hardware. And allowing you to secure the communications and take care of putting protections in place where you really can trust the software that's running underneath the operating system, and protect you even if there's a flaw that develops or an adversary creates malware and puts it on your platform. You're able to keep that from extending the damage across your industrial Internet of Things application or platform. Most of this is done using cryptos, so there's always keys that you need to protect, and being able to secure the boot of that so that you can't have somebody put a rootkit in place is very important, and something that the hardware is being put in place to augment and help with that. And then there's a couple other things you're starting to see to emerge in the software end of things with hardware provisioning of that, and that's the ability to update your keys in devices in the field over the wire. In improving, you know, we talk about manage and monitor everything. Improving the ability to update the software and firmware is critical, as Sid had mentioned earlier. It's not sufficient to have something and expect that you know, if it's in place for 10, 20, 30 years, that it's not going to have flaws identified over the course of its life, or attacks that are perpetrated on it specifically, especially if the device is successful. Being able to do those down the wire over the air updates is going to be critical to ensuring the security of that. And in fact, you see nations are actually specifying that as part of the formula to securing the Internet of Things. NIST just came out with recommendations that everything be updatable over its life cycle. So if we look at how this is being deployed today, what you're really seeing with the IoT platforms are things, functions, really where the business world meets the operations world, and seeing integration of those on these platforms. And you know, we call them device management systems. Some people call them IoT platforms. And you know, they talk about those being in the cloud. It doesn't necessarily have to be in, you know, over the internet. It could be on site, but it's really talking about computing and collecting data, analyzing it, and providing insight that you can do with that computing capability, and really augment what's going on with your machines in the industrial setting, and how you orchestrate that and all the other business applications and services that you're trying to integrate into efficiently running that operation. So right here in this picture, we really start in the middle with the physical world. You've got a robot machine tool center, you know, whatever's running your line. And being able to add some intelligence to that, but then because of the communications capability, being able to integrate that in with other systems. And then on the right hand, you know, you're actually looking at how you do that within the business context. And this is really an architecture that Intel put together with SAP. It's just an example, but you're seeing that this is becoming the dominant kind of design. And then you have device management that's going on in terms of making sure that it can monitor what's going on with the machine, help it run efficiently, and then help it run with minimum downtime by analyzing what's going on with it, and actually doing some analytics and you know, failure repair prediction. But the main thing you're seeing with these the current approach is that you're doing security in an end-to-end way, and it's all software based. And as we've seen over the last couple of years with the examples that Sid just went through, that there are issues with that you are vulnerable to software attacks. So with the rise of hardware security, there's really a way to improve how this is handled. So on the next page here, just looking at an example of how you would do this and take advantage of that hardware security, that's overlay that hooks into that. So down at the bottom, out at the edge, if you will, depending on your point of view, you've got your operational technology working the actual production environment, the industrial Internet of Things. And you've got devices that have been there for a while. You've got devices that are brand new with more intelligence in them. And to the extent that you can start with a hardware root of trust and then build those, you know, 5 things I mentioned to harden the device, on top of that with the secure boot and the secure storage, trusted execution environments, you can ensure that the devices are actually robust against those kinds of attacks, against adversaries. And then, you know, as we see this intelligence move out to the edge, you're also seeing that, you know, you get this hierarchical organization of your industrial facility. You also see that in terms of the management and control of it as well. And so you end up with edge appliances that are you know, multifunction controllers and the applications that run on them. A lot of times these are sold under the moniker of a gateway. And those allow you to provide security umbrellas for the devices under it. They allow you to do the supervisory control, and those also require the hardware security embedded in them. So the other thing that you're starting to see is that they're just like servers did back 10, 15 years ago, you're starting to see consolidations of workloads. The picture we saw of that machine tool center was Sid earlier. We're actually taking advantage of virtualization and being able to do more than one thing with these devices. They're not just single-purpose devices anymore. They're being used in a way that allows them to have the compute power to have the security, and then use that broadly across a number of devices and provide umbrellas of protection for the things underneath them. These also need to be instrumented for security, and you know, at a minimum, you're going to have a firewall, some sort of remote attestation. You know, get rid of those default passwords, and of course the secure communications. And then they're speaking out to the traditional things you had in you know, SCADA systems or supervisory control, and the people that have to work and optimize and run those systems, and really you know, doing the manageability both in-band and out-of-band, and you know, basically moving into the known world of securing the communications and managing and monitoring everything. And then on top, you've got, you know, we call it the industrial cloud, but as I said earlier, it doesn't have to be out on the internet. That can be something that's local to the facility, so that you've got a little more protection from outside influence and attacks. Don't be confused though. If you've got a system that can talk to these systems and it can talk across the internet, that air gap that we think we had between IT systems and OT systems is really gone. So you really need to do security everywhere at all of these levels. And you know, remember, it's not just about data anymore, especially when you're talking about control systems. It's about control just as much as it is about data. And security then becomes an attribute that contributes to reliability. Obviously, if you're secure, you're also not going to have probes that take away performance from you. But in the very end, it's also about safety and even life safety, depending on the system. If someone can take over a robot arm, they could smack somebody walking adjacent to it. If they, you know, you've got life there, they have control over processes. These machines sometimes have dangerous chemicals. I mean, anyone that's doing a refinery or that kind of operation understands there are conditions you simply can't allow. And security is instrumental in providing the safety of that. So let's be specific now and really zoom in on the problem that we're trying to solve here, and that's in terms of getting these devices up and running and within that first minute of life. So I got a little thought experiment for you. I want you to write a number down on a piece of paper on how long you think it would take to securely onboard 10,000 Internet of Things devices in your factory. You know, simple example, just think about 10,000 smart bulbs. Intel actually went through this problem a couple of years ago and looked at how long it was going to actually take to install a bunch of smart sensors. And if you are taking 20 minutes to 60 minutes or more to do that, 10,000 devices is going to take one person 20 months to accomplish. That's not acceptable in a world where that thing is going to get attacked within 43 minutes. The other thing that we're seeing, and the big problem that we see this security, I mean, this is really phenomenal for security. Security usually adds friction to the whole system, and I mean, that's really what's wrong with manual onboarding. It takes forever to get it done right, and as a consequence, you're seeing people either not doing it right or doing it with a lot of flaws. What happens today is you know, your smart device arrives on site, the technician will take it and, you know, install it physically, hook it up to power and communications, and then they'll sit there and try and put keys in the device to secure it. And for a device like a sensor or a smart bulb that has no human interface, they've got to go across some other device to do that. And if you've got a guy that's trying to put a 256 hex character key into a device at the top of a 50-foot ladder, that's a daunting task. And it's no wonder it takes them 20 minutes to 2 hours to do it. The other thing you're seeing is that IT departments are realizing that just like printers in the past have been launching points, you know, beachheads for for adversaries to get into the corporate networks. Internet of Things devices can be that too. So not only do you have to have this person out on the floor putting keys in the device, they've got to be working usually on the phone with somebody in the IT department to get it accepted and credentials into the network that it's running on in the factory. After all this time, you finally get something that starts working and providing data or the control that you're expecting for. Well, there's a better way. And in fact, we're seeing that taking this long is actually slowing down the growth of the Internet of Things. That people, in the example I cited earlier, where we were looking at onboarding 10,000 sensors, we actually found it was going to cost more to install them than for all the devices, and actually ended up canceling the project. We can't do that anymore. We need to be able to take advantages of all the benefits that Internet of Things devices bring to our industrial environments. And we need to do it in a way that's secure. So Intel looked at this and we really saw that a couple of problems. You've got devices that are showing up. It's taking too long to get them onboarded in the system. There's a better way to do that. And actually, building off of that very first principle of hardening a device is an identity, a hardware root of trust. What if you could take that identity and actually have the device reach out and find its owner and configure itself just in time at the point of installation? And we were able to put that together in a solution we call Secure Device Onboard. And it really allows you to pull those together and automate that whole process and do it securely, and in fact, not even have to expose the installer to the keys. So Intel's Secure Device Onboard is dynamic. It takes the device and basically allows a manufacturer to provide a basic image. Only have to track one SKU. They don't really care which cloud it's going to be installed into, because they know at the time of power on, it can actually reach out, find its owner, and have that system configure the device exactly to the software it needs and the security keys and updates that it needs. And even, as we talked about earlier, the attack on the internet because you didn't have default logins, passwords turned off, it'll even allow you to turn those off and be up and running in less than a minute. Intel Secure Device Onboard is really about enabling any device to any cloud. We launched this last year, and we've been working on this to basically separate the enablement of this industry so that device manufacturers can put Secure Device Onboard into their devices, ship them, and then the cloud systems, the on-premise systems, can put it into there and then independently expect that they will work. And the way we do that is really by having a rendezvous that Intel stands up, the Intel Secure Device Onboarding. You create the device, it sends a digital title to the owner, and they use that to register with the cloud system that they want to manage it. And it reaches out and creates a reservation with the Intel Secure Device Onboard service. When that device powers up for the first time, it reaches out. The service does an attestation with the device based on identity included in the device from a hardware root of trust. And if that's satisfactory, then it will pass it on to the address given to it when the industrial cloud registered. And it will introduce that device to the cloud system, and the cloud system will and the device will work with each other to do a two-way attestation. The device will prove that it's a genuine device that the cloud's expecting, and the cloud will share that digital certificate that it got from the manufacturer, and assure that the key that's signed with matches the private key that's embedded in the device. All of that happens in seconds, even on the slowest of devices within a minute. The thing that's interesting about this is that you actually can track the device through the supply chain without ever having to power the device up. So you actually don't have to worry about people intercepting devices and inserting their own credentials along the way. If this device gets out there and someone has put their own credentials in, it simply won't install itself into the cloud service. And then really from a installer's point of view, they're not using any keys. We were working with one manufacturer in India, and they were installing things in a smart city environment. And, you know, they're basically up on the top of street lamps putting equipment in. And we just was talking to one of the guys running the project, and I said, so how long is it before you think these guys doing these installations are going to actually start selling the keys at the bar at night? And he immediately said, well, that's already happening. So by taking that out of the hands of your installer, you actually create a more secure environment. And then, you know, you're able to do that in such a way that the network controller is satisfied and given the credentials you need. And then, you know, we call it an ownership proxy, but this digital title allows you to do just-in-time binding of the device into the system. So with that, I'd like to, you know, we talk about what's essentially the first minute automating that security in the device. I'd like to turn it over to Dean at this point and have him continue on with how they, as one of the first services we work with to enable in this any device, any cloud, how they do lifecycle management of the device. So, Dean?
If you're just tuning in, you've been listening to Guy Ali, Product Manager, Internet of Things Security at Intel Corporation. And now we're going to turn over to Dean Weber, who's going to be talking about the automated security lifecycle management. Dean comes with 42 years of experience in information and physical security and is the Chief Technology Officer at Mokana. He spent several years in the U.S. Navy working with physical and electronic security and is a frequent speaker in information security events such as InfoWorld, ITech, InfoSec Europe, InfraGrad, Secret Service Security Roundtable, IoT World, and IoT Evolution, and various cybersecurity engagements. Dean, welcome.
Thank you, and thanks for watching our show today. So what I'm here to do is to take it from where I left off with the device identity, and then how we take that up into the operating system identity and the secure components of the operating system, and then on up the stack into the application stack to include the concepts of secure virtualization and containerization. And then on the other end of the spectrum, how do you manage all those certificates? How do you provide for a secure update facility, et cetera, et cetera. So the life cycle itself is pretty well designed. It's just not well implemented. If you look at the standards,
Dean, if you want, you can go full screen on this.
Okay. Sorry, I thought I was. No, there we go. Sorry. Thank you. So anyway, the security lifecycle of the device, like I said, is pretty well defined by all kinds of different regulatory events. As we mentioned earlier, IIC's got some stuff out there. So the concepts have existed for quite a while. The implementation of those concepts is not quite as easy to accomplish. There's lots of moving pieces. There's lots of change of ownership between devices, between the subcomponent developer to the component developer to the subsystem developer, et cetera, and then all the way out to the owner operator. How do we do all of that? How do you manage all those certificates? And again, as we talked about earlier, doing that in a manual process is not a very good idea. So what we're here to talk about today is how do we take all of that onboarding and attestation functions and then turn it into operational security management for the life cycle of the devices. The idea is that we have a couple of different components here. We have to take into concept that the device itself has a trust stack, and then that the device surfaces as they present themselves to the network or other external influences also have some issues associated with that, starting from the hardware stack, working up through things like the BIOS, boot structure, on up into the applications, and even up into the executables, are how you create a trusted stack. And again, this is changing the security paradigm a bit from detect and respond to prevent, because we're using cryptography and trust chaining to accomplish these functions at whatever level or strength of crypto is appropriate for the environment. And again, that may change depending on strength of processor, that may change on forms of anchors and other forms of offload encryption functions like hardware acceleration or TPM or TE trust zone, where all these functions can be managed at various components so that they are optimized for a particular environment. And then on the right side, this is where we show that those hardenings of those functions actually work in reality, where we have that concept of a trusted or a protected boot structure. We go on up into the operating system, which would be the virtualization layer or the containerization layer underlayment, and then into the VMs or into the containers at that virtual edge, and then on up into the actual data structures and how do we convey that across the network. So we have two technologies that we bring to bear. As I said, with this, we have a concept of a product that's called TrustPoint. TrustPoint is a application stack that gets embedded into the target platform through compile time options. There are various components that we can bring to bear there. But what it does is it allows us to have a basic construct of an endpoint at an appropriate level, from reasonably secure 62443 3-3 level 2 on up through very, very secure with a 62443 3-3 level 4. And all of that is dependence on the types of trust, the types of root of trust, the strength of the components, et cetera, when you're talking about industrial automation and industrial security. So again, the benefits of all this is that you get a trustworthy device that is immediately discernible if there are any modifications to the device, because we're using cryptography as the form of measurement, and we're using an endorsement process to endorse from that root of trust that has been established by things like Intel, SDO, and EPID on up through the BIOS functions, the boot functions, et cetera, so that what you end up with is a cryptographic value that represents the trustworthiness of the platform. And that is conveyable. It is attestable to both locally and remotely. And therefore, not only can trust be established upward from the device to its next communicator, but it can also be validated downward. So that basically, if you include transport into the equation, what you can do with this is you can say only trustworthy devices can talk to trustworthy devices. And they both have to agree that the other one is trustworthy. And we do that using a very efficient mechanism built into the cryptographic functions that is endorsement and certificate management. The stack looks something like this, where we have whatever the root of trust is at the bottom. We have whatever acceleration may be available, if that's hardware or firmware or even software. We have whatever the trust anchor is going to be, and whatever the processor architectures is or are. And if this is an FPGA, then great, we do this on an FPGA. And if this is a distributed processor architecture, or even if this is up into an Intel I-series processor where we have AES and I functions that may be available to us. So there's a lot of things down at the root of trust that have to be considered and utilized properly and managed properly. And then above that, we get into where we abstract all of that, because you don't really want to have to go through 400 pages of TPM architecture, as an example, to figure out what your root of trust is going to look like. Intel has certainly simplified that with the SDO and EPID process, but that gets the device identity established. That doesn't take you all the way up the stack in terms of measurement and validation. So getting to that device and data integrity starts with an abstraction layer from a Mocana point of view, because we don't want that to be something that engineers or developers have to rewrite every time something changes, going from TPM 1.2 to 2.0 or future revisions. Same thing with TE Trust Zone as we head into the PSA world, and all the ARM PSA architectures that are going to spin out of that. I mean, there's lots of different changes that are being made, lots of different processor architectures, FPGAs, ASICs, et cetera, et cetera. So what we try to do is we try to abstract that so on our part, we don't want to have to redevelop to all that. So we create a plug-in architecture at the bottom of that. And then above that, we create a standard set of APIs that we use and we also make available to our customers. And that gets you into the secure boot, the verified boot structures. That is the basis for the secure updates. And then again, as we talked about, the transport mechanisms and then the authentication and non-repudiation functions of things like IIoT with all the new NIST guidance on, let's call it pre-post-quantum world of quantum resistance in terms of key padding and in terms of functions associated with entropy, internal and external entropy. So all these things are brought into play, and then over on the right-hand side, we have our validated crypto engine at FIPS 140, and then we provide not only device certificate management on the device via standard OCSP and SCIP, we also, as we'll see here in a second, have that in a services management platform where we're using newer, stronger protocols like RFC 7030 and enrollment over secure transport. So that is Trust Center. And Trust Center is a mechanism by which we can take like the SDO process. Once the device has an identity, we at RSA this year demonstrated where we can put our enrollment and update agents over the top of the SDO UUID provisioning. So when the device gets assigned its identity, it gets our agencies as well, so that we can then start the certificate provisioning process above SDO for things that are elemental to the secure boot architecture, the BIOS architecture, the operating system or operating platform architectures, et cetera, et cetera. So the idea here is that this can scale all the way up. Using Intel as a basis, we're zero touch, right? Using our own technologies as a basis, we have to be one touch because somehow we have to get our agent onto the device. We can still do similar things where we can validate the identity of the device in a bidirectional fashion before we allow it to be starting the trust process. However, it is still that one touch, whereas with Intel SDO, literally we can be zero touch. Again, all kinds of benefits in terms of how does this snap together. In using these types of models, you can actually maintain the efficacy of the supply chain from that element component all the way through the system deployment and then ultimately transference to the owner operator. You can do this in a very efficient method, which lowers costs and develops or provides for faster development. It's a multi-factor verification. We can assign 2 or more signing values to every operand, so that the only way that take an update, as an example, can be delivered is done by a 2 or more signage rule, which solves for a number of the updates that are the problems that are out there in the world today, where sign and hash is just insufficient to the task if that key is compromised, or that certificate is compromised, or that CA is compromised, all of which we've seen in the not too distant past. So these concepts of 2 or more man rules have been in the military for a long time. You'll remember the War Games movie at the beginning where the 2 guys sat in the missile silo and had to press the button at the same time. Well, that's a 2-man rule. Both people have to agree that this is appropriate to do at this point. And the update process is no different than anything else that we do. So we have a policy engine that can help you deliver that and then help you enforce that, report on that down the road. All right, so this is what it looks like when you all bring it all together with Intel SDO. We have the zero touch provisioning, which is basically the SDO client as described. And then once that is done, we can move into the provisioning of our onboarding agents, and we can actually then start provisioning the certificates. And again, one of the values that we bring is we're Switzerland. We don't care what's at the back. It could be a CA attached to AD. It could be a cloud-based provider like Digi or GlobalSign. It could be an on-prem like PrimeKey. It could be a homegrown internal certificate authority. It could be an HSM. It could be any combination thereof. And as long as we have read-only access to the back-end data services to do certificate root validations, we can make sure that those certificates are currently in good status and able to be used. And then from there, once we start the enrollment process, whatever we're going to put on that device or whatever is already on the device, if we're going to take an image down to it, if we're going to take a VM or a container down to the virtualized platform, we can then start the provisioning process associated with that. We can start that remote attestation process once we have provisioning started so that we can validate that what we expect to see on that device cryptographically measured is indeed what we see on that device cryptographically measured. And then as we go up from there, all of that function is available back to the back end in terms of the analytic providers and all of the industrial cloud architectures at the back end. So if you're taking that out to Predix or you're taking that out to Echo or one of the other architectures that are out there for that second and third stage analytics, we can certainly facilitate all of that. Okay, so a couple of quick use cases, remote device onboarding in an oil and gas model. Obviously, the problem is a distributed sensor array across a wide variety of products. The solution is at power on, either through something like SDO or another process, we become aware of the device, we provision the device, and then we start with the operational transaction measurement of the device so that we are not only sure that it's trustworthy when we power it up and begin to trust it, but so that its life cycle is trustworthy. If a certificate has to be replaced, or if you want to decommission a certificate or add additional capabilities to the device, all of that can be done in a very automated, a very effective fashion. And again, the value of that is immense when it comes to the distributed security architecture of how you actually would accomplish that. Second use case is factory floor provisioning. Very similar use case, again, using the SDO mobile function to actually bring the device up. This could be as I pointed out earlier, this could be a battery-powered device that may come on, enroll itself, validate itself, get loaded, become trustworthy, and then at the end of the day, go back to sleep for a period of time until used. We had one where we had emergency stop sensors on the shop floor, where literally the device had to have a 10-year lifespan on battery, and once a month it needed to come up and validate itself using a cryptographic function, which we supported. So again, this is the overall function of how we do this. This is actually Intel's slide on how the provisioning works out. And I believe at this point I am turning it back over to Guy. Is that you?
Yeah, so you've been listening to Dean Weber at Mocana, the Chief Technology Officer, and we're now entering the final session of the program, the panel discussion. And for that, we invite Greg Orloff, the Chief Innovation Officer at IIoT World, to moderate the panel. Greg has served as the CEO of Tangent Company, and it's got a Bachelor in Engineering as well as an MBA from Case Western Reserve. Welcome, Greg, and we invite all the speakers to unmute themselves for the Q&A session.
All right, thank you, Lucian. I guess first and foremost, thank all of you attending today, because we've had a barrage of outstanding questions. And I'll start off by prefacing this, that we will try to address as many of these as we can. But if we don't get to your specific question, then fear not. We're going to share it with the panel, and someone will circle back to you, most likely via Twitter. Can you confirm that, Lucian?
Correct.
Perfect. So without further ado, let me dive into some of these, and I'll start to work on, I think because the Mocana presentation is most recent. We had one specific one for that. This is from Elliot. It says, does the certification process rely on exposing the IP address?
I guess I could take that one, and the answer would be no, but it would depend on how you were actually onboarding the device. If you're relying on the IP address to be part of the device identity, then yes, that identity would be a function of the IP address assigned or fixed to the device, but that is not a requirement. There are ways that you could use other than IP addresses as a component element, such as the way that SDO is actually designed. You could be doing that across other forms of networking that did not require a fixed IP address.
Okay, perfect. Thank you. We had several questions come in. This is a little bit more into the technical aspects, but could the speakers share insights on alternatives to PKI and X509, which is fundamentally complex, even with zero-touch provisioning? Besides, PKI was never designed for scaled industrial IoT use cases. Does somebody want to address that from Sravani?
Well, so this is Guy. I'll take a whack at that. So, I mean, PKI is really a well-developed model for doing public key infrastructure. It's a way to provide attestation, and really that's you need to have attestation in there. I mean, your PCs and servers, are relying on login password. For in a machine world, they're not people. Attestation is really the way to do that, and PKI is a known standard to accomplish that. And there are varieties that are complex, like we've been using with asymmetric crypto, where it's you've got two one key that you can encrypt with, one you can read with. There are simpler forms of that called symmetric crypto, and the interesting thing is that once you've established the initial connection with secure device onboard, you've actually left a secure tunnel behind. You can provision shared secrets, symmetric crypto, asymmetric crypto down the wire over that secure tunnel, and securely provision those keys into the devices automatically and programmatically, rather than having to try and put those in by hand at a device, which is a lot of people just skip nowadays.
So let me add a little bit more to that. In general, two things. Number one, this PKI X509 architecture that we have available to us today is designed for a large-scale deployment, and why things like RFC 7030 are becoming so prevalent in the certificate and PKI architecture world as a means to provide for those certificates over the wire or over the air. It's also recognized by government, right? So if you look at FIPS 140-2, which is now a requirement for all government agencies to be communicating above unclassified. And this isn't just the U.S. government. There are many foreign governments that have very similar rules. So it is a recognized international standard for both certification and for utilization, and it becomes an easy way for everybody to understand how the cryptographic handshake needs to occur. Now, that being said, there are a number of non-X509, non-PKI architectures out there. And at the end of the day, basically what's ending up happening is those are unique device identifiers. They are proprietary, and the only way that you can get them to work in a homogeneous or heterogeneous environment is to actually assign certificates to those unique values. So I don't see us getting away from certificates and X509/PKI architectures for the foreseeable future, although the post-quantum world offers us all kinds of opportunities to do interesting things.
Excellent. Thank you, gentlemen. I had a couple questions, and this one on Noah, as well as several other folks tabled something of a similar nature. Is the effects of spyware been taken care of in this type of an architecture of interconnectivity? So I know we talked a little bit about ransomware. I think you did, Sid, but does anyone else want to address spyware and maybe some of the other aspects?
Again, I can. What we've demonstrated here, or what we've proposed here and discussed, is the ability to cryptographically prove that an element has not changed from an expected value standpoint. It's beyond whitelisting, right? When we're taking cryptographic measurements of elements as expected, and we are able to convey those to appropriate consumers that can then validate or revalidate those values are the expected values or the trustworthy values. This is the basis for trustworthy computing. I would tell you that, as long as the code has not been tampered with from creation, when we first measure it, all the way through to the deployment, that yes, the spyware issue or any other modification of the code would be detected and invalidated. Obviously, at the DevOps or the DevSecOps models, you still have to take appropriate care in those models to make sure that you don't implement something at creation.
Yeah, and I mean, this is the things we've been talking about today is really, part of a balanced breakfast, right? These are necessary steps. They're not sufficient, but we certainly know what we have to do to make sure that we can keep spyware out of systems, and as Dean alluded to, we actually use cryptographic measurements to prove that they're not there.
Yeah, this is Sid. I mean, I don't see that it's a major difference than other kind of vulnerabilities, other kinds of attacks. It's just that we're all afraid of it. But everything they just said, both Dean and Guy said, I think are exactly right. And one of the things we see in industrial cybersecurity in general is this idea of doing dumps of what the system looked like today and making sure that it stays that and that detects that kind of stuff.
Yeah, and I really appreciated Sid talking about the SANS Institute. They did a pretty good analysis of the cyber attack in Ukraine. That's very instructive, and I certainly recommend anybody who's worried about this to have a look at that paper. It's pretty short, I think about 16 pages, and really covers the state of the art in terms of what your adversaries are thinking and what you need to think about in defending your industry from these opportunists.
I had a question more along, I guess, the implementation side of this, coming in from Hussein. This is an opinion question, so we may get some differing voices here, but is an all-at-once deployment across all applications, devices that are connected to the network better, or should you look to do a gradual phase-in?
I'm happy to go first. It depends on your deployment model. I mean, if we're talking about a common containerized application that needs to be deployed to 10,000 devices, then we deploy the image. We validate the image, we give the image access to a secure platform, we revalidate the image on the secure platform, and then we convey that trustworthiness through cryptographic measurement. If you wanted to do that on an application by application basis, it works the same way. We're still going to deliver the application to the platform in a secure fashion. We're going to validate that the application that was supposed to go indeed went. We're going to validate that it was put into place, that it was measured properly, that it was operating properly, and then we're going to add it to the trust stack, add it to the trust value, and then revalidate that trust stack in terms of the overall trustworthiness of the platform.
I'm not sure exactly what the person who asked the question was referring to, but I mean, what we see with the client, most clients we have a lot of clients, and we're all industrial clients. From a deployment, if the question's about deployment of IoT devices and deployment of digital transformation initiatives and things, most companies are doing that in an incremental way. They run pilots, they'll try a small version, and then if that works, then they roll it out to other factories. A lot of our customers have, factories around the world. So they'll do it in one plant, and then they'll do it in another. If that was the essence of the question, so I don't know exactly what, but that's how we see them actually deploying IoT devices. And they're very careful. Industrial world is very conservative. They're very careful about making sure things work before they roll them out.
Yeah, I think the most important thing is simply be aware that you should be taking care of this, right? And even a little bit's better than none. Start somewhere and build out to that full protection.
Yeah, and there's absolutely a crawl, walk, run that could be done there. So, again, it really depends on the deployment model and the outcome desired. If you're replacing a sensor grid with a lot of new sensors, and you want to do that wholesale, these technologies can certainly be brought to bear. If you have an existing brownfield environment that you want to upgrade and you want to displace things like username, password with certificate-based authentication as the starting point, we can certainly do that as well.
Perfect. We had several questions also come in around around fog architecture. There was a couple people that were looking for some clarification. How does fog factor into this? You know, what layer would it be integrated into? And then also, if you could give more details on the edge appliances used with VMs of condition, predictive maintenance, HW security. So there's still a little bit of a question out there on those topics.
Yeah, so I mean, fog is really about moving some of the compute out really close to the sensors to the edge, and you know, with that capability, with that approach, you actually provide the capability to do more things analytically and control-wise out closer to the actual sensors and effectors in the world. And you're going to want to deploy those assets with the same kind of protection that we've been talking about with respect to the sensors all the way up to the cloud. It's just it's really just distributed intelligence, and you're going to want to do the same things in the security realm.
Yeah, I would comment, you know, from a lot of our clients, there's a lot of issues in, again, the industrial world I live in, that people are, even though everything's shifting towards the cloud, people are saying we don't want to open ourselves up that much. So people are using this deployment of more intelligence down to edge devices, which is, I guess one could call, I mean, fog is a very general concept, but deploying more intelligence down to edge devices, I think, is an element of it. And we're seeing that happening for lots of different reasons. I mean, some people will do that just because they're inside a plant. They don't want to connect a bunch of devices just up to the cloud, but they'll want to connect it and use collectors and aggregators, and as well as do local analytics, because they don't have to worry about relying on the cloud and things like that. So there's a lot of drivers to do that, and it's certainly a trend we're seeing. You know, there's also the issue of just cloud capabilities anymore, and then timing and things like that. But I personally, I agree with what Guy just said. I don't think it changes the security issue, whether you do it within an environment, or within a plant, or within a controlled situation, or going to an edge device. You still have security issues, and you want to get that is just the same almost. It's maybe it's a little different than being out on the internet, but it's still a very insecure situation. You have to make sure that you have security addressed within that, whatever deployment you take, whatever architecture you use.
And I'll say amen to that in spades. You know, the concept of fog is not new, right? I mean, we've been doing V2X, we've been doing machine to machine, we've been doing mobile to mobile, we've been doing peer to peer for a long time. The idea of sharing resources across a local area connection, or even a wide area connection, has been around for a long time. The question is, how do you do it safely? Because at the end of the day, when we're in industrial, safety is job one, right? When things become unsafe, untrustworthy, they can potentially cause loss of life, which is why the focus on this is so stringent on the safety aspects. But so there's you know, everything from group keys and GDOI, and the ability to do this in a very lightweight encryption that occurs over an encryption domain based on group keys, which is a single KDC and a bunch of identical public keys, all the way out to actually doing full-blown integration in an edge platform, like a gateway type service where there's a layer of virtualization and there may be multiple workloads sitting on that device that need to intercommunicate amongst each other. That's essentially a fog platform, right? So, I mean, there's tons of implementations of fog. I guess to the point that was made earlier, they all have to be secured in some fashion, and security has to offset reliability and safety and usability, et cetera, et cetera. So that's my 2 cents.
Great, thank you. I think you've got a couple questions here. There's a two-part one from Ravi. It says, do you have any input on insecure protocols like LAN or BACnet? And the second part of this question is, what's the current industry trend and what work is currently being done to move all industrial controls communications to secure communications?
Well, I can comment on that, though I'm sure the others can as well. But we see an awful lot of LAN and BACnet things, particularly in buildings. That's where those are very popular, as well as in smart cities and things like that. You're seeing a lot of a lot of protocols. There's a lot of protocols in industrial plants that are designed, insecurely designed. They were never, they have no capabilities to do security. And, you know, where people can change those, I see them changing them today. You know, there's a big trend to doing more things like taking the insecure protocol and embedding it within an IP kind of a protocol that is secured and things like that. But, you know, there is this big issue of legacy devices without the capability to deal with those types of security issues. And so people are doing wrappers around that. You know, at most companies I know that everybody would love to replace their equipment, but it's a very difficult thing to replace. You know, it costs millions of dollars in downtime, and as well as a lot of downtime to go replacing control systems. So often they're putting in containers around it, they're incrementally upgrading them. The example I gave of that control system earlier, the modern control system, is this push towards an open automation platform that really is trying to address that issue of not being able to increase. So it's really trying to address the issue now of the insecurity is one element of it. Another element is just the cost of maintaining the systems, but it's a new architecture. It's trying to push things to a new architecture, and one of the big drivers of that was Exxon, who faces the replacement of a lot of systems in the future. So it's something everybody wants to do. Those protocols are there, they are insecure, and you have to kind of address them item by item, you know, I mean, by issue. And generally, it's really kind of a wrapper or compensating control.
Yeah, and you also have the capability to use some of these, you know, the fog architecture, the cloud architecture, to put security analytics in place as well. I know that a couple of years ago we were working on a smart grid test bed in Texas, and we installed a system with, you know, all of the stuff we were talking about here, harden the devices and secure the comms, and actually put in managing and monitoring. We installed the system and turned it on, and immediately you're getting alarms all over the place. And it was the first day of the Heartbleed attack, and it wasn't that we'd screwed up the software, it was that there was a real attack going on. And because of those security analytics, we were able to detect the problem immediately. And because of the policy engine that was behind that, we were actually able to put a policy in place that protected not just the node we found it on initially, but all the nodes in the network within an hour. And the rest of the world had to wait 14 days to get a patch for it that some people still haven't put in place today.
Yeah, with an average of 40 days to install.
Yeah.
Let me take us in a different direction. There were a couple questions that also came up around, I guess, how do you do implementation on this and frameworks? And Jibin actually wrote, is there a framework or standards followed for doing security in the right way? So perhaps somebody could talk to some of the, you know, regional, international, you know, standardization efforts that are currently in place, and then where some of those gaps are and what efforts are being made to fill them.
Are they, I don't know, I can answer generally from the industrial side. I mean, you know, there's frameworks. I mean, there's the NIST framework, which is very popular today. There's IEC 62443 that's used by many, many companies. When I've done my surveys, that's probably the most dominant one. You know, there's there's special standards in Europe. There's standards in the nuclear industry. There's standards in the power industry. NERC-CIP is a very big one there, but they don't cover everything. One area they miss is distribution and things like that. So there's a lot of frameworks and standards out there for securing industrial systems, but none of them that I know of. I mean, there's just starting to get into, and maybe Dean can comment more and Guy can comment more, you know, from the device security side. I mean, we see the IIC is coming out with a framework. That's one. I know there's other ones probably being developed, but but this whole supply chain, I don't know that there's a standard there yet. In that, I don't see it addressed in many of the standards I deal with, which are kind of higher level. It's more focused on protecting legacy systems than it is implementing new systems. But
so again, I agree with all that was said. And then there's, you know, guidance coming from things like the IIC. There's also guidance coming out of ISA 99, which is the fancy part of the ISO IEC 6443 standards. so there's a lot of that going on. There's also, in the government world, specifically around NIST, 800-171 is a group of guidances about how to create a supply chain system and how to evaluate it, and the elements of that are now being put into DFARS, which is the Defense Acquisition Requirements, where you're going to have to be able to prove the efficacy of the downstream devices. And again, that's likely to be a cryptographic function because that's the easiest way to manage active and discrete components as well as softwares. So there's a lot coming, but I don't know that there's a single standard I can point you to that say this is everything.
Yeah, and I think in general, if you've got an industrial standard that applies to your industry, that's absolutely the right place to start. But in general, I mean, all of these are really, it's a risk analysis and management exercise around security. And your first step's going to be to assess what you've got, what your vulnerabilities are. And the thing that's really interesting about that is you'll identify the cost of insecurity that you can use with your management to help you motivate them to pay for these improvements.
Okay, thank you. That question just came in from Justin. It says, and this is to Mocana, is there any Mocana integration with network access control systems available today from Forescout, Cisco, ISE, and a whole bunch here? We see some companies wanting to implement NAC just for visibility, not necessarily to control network access.
Well, I would give you the short answer of, if you're using trustworthy computing tenants, which means that you are evaluating on a connection by connection basis the trustworthiness of the communicating devices, the network becomes plumbing. So there isn't a lot of request of Mocana to integrate to those. Now, that being said, if there was a specific use case, we're a venture funded startup. So if you point us to money and you tell us you want us to do something, depending on what the value of that transaction is, we certainly could integrate into any of the NAC or CNAC type architectures. Same way with the network architectures, right? So the establishment of things like DRF or even VLAN participation. But going all the way back down into the industrial network, we're not seeing a lot of that coming out of the industrial network yet. That's still pretty much an IT function, not an OT function.
I agree with what Dean just said. With respect to that not being as much an issue in the industrial space, even though it's an issue that's just not a focus area, and it's much more an IT issue than it is an OT issue.
There's a couple of questions that came in, and I'll throw this out there, that the whole panel around speed and software and operational efficiency. Can you guys comment to how hardware security, in addition to software security, will impact connectivity speed, and will that be a binding constraint, in your opinion, for timely decision making?
Well, I think one of the things that we actually grappled with was just the basic inconsistency between trying to do something with a very small, simple microcontroller versus having the compute power available to do true security. And what we ended up with Secure Device Onboard is using a very high secure method of doing your initial establishment of trust, and then allowing identity management like Mocana has to actually replace that with something that's much simpler for the device and quicker if you want to do that. And I mean, you can go from this whole, we use Enhanced Privacy ID, which is a group elliptic curve solution. You can go from that, once you've established that hardware root of trust, then you can go to much simpler, faster ways to do your security, say symmetric keys, and then change them often. I mean, you've got that ability to manage that over the rest of its life cycle.
Okay. Hussein has a question here. He says, which of the four sections of the new industrial architecture is the bottleneck? And in what sense do you consider it a bottleneck?
Can you repeat that? I didn't understand.
Sure.
What four sections?
Yeah, I'm trying to think if this, it came up earlier in the session. So which of the four sections of the new industrial architecture is the bottleneck?
Well, I'm still confused, but you know,
Yeah.
the bottom. I mean, if it's referring to what I just said, you know, I mean, I think a bottleneck is very much down at the bottom. You know, I mean, it's because people can go and they can implement new cloud systems. They can buy IoT platforms. They can do stuff like that. They can buy new devices to add, but they can't very easily change existing things that are there. So that's one of their big issues. And again, you know, to justify the cost of replacing an existing control system can be very difficult, whether it's a control system in a power plant or whether it's a control system on a mining truck. It's still a system that's there, it's working, and those companies are in the business of mining, not maintaining security. So getting those things changed out, I think, is a big hurdle. The other one that I didn't mention, I mean, I don't know how relevant it is to our topic today, but it's a very big issue, is just the lack of expertise of people, cybersecurity people. There's a major problem in the industrial world. It's a major problem everywhere, but in the industrial world in particular, you just aren't enough people to implement all these things.
Okay, excellent. Well, gentlemen, thank you so much for the insight, and thanks everyone in the audience for some great questions. I know there were probably several in here that were more topic specific, but we'll circle back to you, as I mentioned, either via Twitter or via direct message, and we'll get you the answers that you're looking for. So at this point, I think we're going to conclude our question and answer session. I'm going to turn things back over to Lucian.
Yes, thank you everyone for joining. Just wanted to remind you that if you'd like to get more details on this subject, you can visit the Intel's website that's listed here on the Intel Security Device on Board, as well as the Mocana Trust Point and Trust Center. Also, you can send an email to the IoT onboarding.intel.com. Actually, you can visit a site there. I also wanted to remind you that we do have a series of educational programs around industrial IoT, from predictive analysis and maintenance, that's coming up in the next couple of months, as well as on Grid Edge, capitalize on disruption by turning the challenges of changing the energy landscape into profitable business potential. So with that, this will conclude our program. Thank you everyone, and have a great rest of the day.
Hey, thanks.